Everybody. Okay, let's solve this problem 3 different ways because we're trying to find the centroid of this composite, and I'm calling it a composite because it looks to me like there's a triangle here, and then a rectangle here, and then another triangle here. So that's one way we could do it. Another way is it looks like a big rectangle with a cutout here and a cutout here. And then a third way is we just brute force integrate. So let's start with the composite of the 3 things. And it looks a little bit like 2 triangles like this. But I think if we run the numbers, this distance is a little bit shorter than 12.5. So let's give it a try. So let's work out the geometry. Let me make note of the coordinates here also. So we have x this way and y this way. And we have 48 degrees here, which is the same as here. We have 70 degrees here, which is the same as here. And then the location of the centroids for the rectangle is just right in the middle. For this triangle on the right, it's kind of right over here, where this is 1/3 of the way this way, and then 2/3 of the way this way. And then for the triangle on the left, the centroid is right here, where this is 1/3 over here, and this is 2/3 over here. Okay, so let's figure out a little bit of the trigonometry. So this is 11. This is 12.5. So let's call this x1. Let's call this x2. And let's call this x3. Okay, so for x1, let's just look at that triangle here. So we know this angle here is 48. And we know this. And what is this? Tangent 48 is opposite over adjacent. So that means x1 has got to be 11 tangent 48. Okay, so we got that triangle figured out. How about the other triangle? This one. So we got this angle here, and then we're looking for x3. We already know this is 11. So tangent 70 is opposite over adjacent. So that means x3 is 11 over tangent 70. Or you can say 11 cotangent 70. Okay, and then the rectangle, since we already know that here to here is 12.5, and here to here is x1, x2 has got to be 12.5 minus x1. Okay, so we got the geometry for all 3 shapes. Now to find the centroid, we just do the area weighted mean position of the 3 shapes. So for let's start with this triangle. So here to here is 2/3 of x1, 2/3 of x1 times the area of the triangle. So 1/2 base times height. Okay, now rectangle, here to here is x1 plus half of x2. So I'll just write that down. x1 plus half of x2 times the area of the triangle. So base times height plus, now for this triangle, here to here is 12.5 plus this. which is 1/3 of x3. So 12.5 plus 1/3 of x3 times the area of this triangle, which is 1/2 base times height. Okay, and then now we just divide by the total area, which is this and this and this. So, right, that's the area of this triangle, the area of the rectangle, and the area of this triangle. Okay, let's try the y component. So similar, right? Here to here is 1/3 of 11 times the area of that triangle. It's just right here. Plus here to here, which is just halfway, times the area of this rectangle, plus here to here, which is 2/3 of the way up, times the area of this triangle, which is right here. Right, divided by the total area. Just copy and paste that right here. Okay, so then we got the location of the centroid this way. So now let's try another method. It looks like one big rectangle with a cutout here and a cutout here. And cutout meaning negative area. Right, so then we're left with this shape, the vertical stabilizer. So, and then let me get the dimensions back here, right? We figured that all already. That was x1, this was x3, here to here was 12.5, here to here was 11. This was the x direction, this was the y direction. So if we want the centroid of the entire shape, the rectangle, the centroid is in the middle. For this triangle over here, for this triangle over here. So let's start with the rectangle. So here to here is half of the entire rectangle. So half of 12.5 plus x3, and then times the area of the rectangle, 12.5 plus x3 times 11. Okay, and then now the first triangular cutout here on this side. So here to here is 1/3 of x1 times the area of this triangle, which is actually negative 1/2 base times height. Right? Negative because it's a cutout. Plus, now here to here, so that's, let's see, 12.5 plus 2/3 of x3. Right, here to here is 2/3 of x3, here to here is 12.5. Times the area of this triangle, which is negative 1/2 base times height. Okay, and this is negative. Okay, and then divided by the total area. So the rectangle, which is right here, plus this area, which is a negative, plus this area, which is negative, because it's a cutout, negative. And there you go. That's the, punch that in the calculator, it's the centroid, the x component of the centroid. And then for the y direction, kind of similar, for the entire rectangle, here to here, half of 11 times the area of the rectangle, which is this, I'll just write area of the rectangle, which is here, plus here to here, which is 2/3 of 11 times this area, which is negative, plus here to here, which is 1/3 of 11 times the area of this, which is negative, right? It's a cutout, negative, 1/2 base times height, divided by this exact same total area. Okay, and you'll get the same answer as the previous way. Okay, now let's try a third method. So let's just brute force integrate this thing, which maybe isn't as bad as it sounds. So I think I would prefer to just rotate this clockwise. So it'll look more like this. And then I'm going to pick new coordinates. I'm going to make this X and this Y. It's the same shape, right? I just changed the coordinates. And then here to here is 12.5. Here to here is 11. And then the angle here is 70. And the angle here is 48. Okay, so if we want to find the centroid, we're going to have to, let's say if you want the X component, you have to integrate like this. But then we'll need the limits of integration in X and Y. So in the Y direction, it's like going from this function to this function, like from Y1 to Y2. And in the X direction, from here to here, from 0 to 11. But what is Y1 and Y2, these functions? So if you just do like slope-intercept form, the slope for Y1 is, I'll just draw it over here, rise over run, right? Which happens to be opposite over adjacent to the angle, which tangent is opposite over adjacent. And that's the slope. So the slope is tangent 48. And then the y-intercept is 0. So this is the function. Okay, how about this function? What is the slope? So I'm going to do the similar. In this example, the triangle looks more like this, where this is 70. And then we want rise over run for the slope. Right? Rise over run, which is adjacent and opposite to the angle. So that's actually the reciprocal of tangent, right? 1 over tangent 70. So that's the slope. I'm just going to write cotangent 70 just for less writing. That's the slope. And then the y-intercept is right here, 12.5. Okay, so now we got both functions. So then if you want to find the x component of the centroid, you just have to get this numerator, this denominator, and then for the y component, like that. Okay, let me set one of these up. So how about I'll do the denominator. Right, so dA will split into x and y, dy, dx, where y goes from here to here. So it goes from tangent 48x up to cotangent 70x plus 12.5. And then in the x direction, from 0 to 11. Right, so if you integrate dy, turns into y from y1 to y2. So if you evaluate that, y2 cotangent 70x plus 12.5 minus y1, which is tangent 48x dx. Okay, and then you integrate this, right? That'll be cotangent 70x squared over 2 plus 12.5x minus tangent 48x squared over 2, and then you evaluate that from 0 to 11, and so on. If you wanted to do this one, xdA, everything looks the same, except there's going to be an extra x term right there, which shows up right here, shows up right here, and then similar process. And then if you wanted this one, then there's a y that shows up here. This becomes y squared over 2 when you integrate. And then when you evaluate, it's going to be this squared minus this squared. And then you evaluate, integrate that, and then from 0 to 11. So keep studying. I'll see you on the next video.